Okay, so we'll get started. So today we'll continue on in flow control. We left off, I think, talking about if statements, and now we can add else and other stuff. Talk about loops, and then we'll get into functions, and we'll see how much we can cover as far as functions go. I posted your second homework assignment. That will be due 1 week from Friday. That's October 20th, okay? It's, well, depending on how much background you have in programming, some of you might find it challenging, okay? The second half of the assignment requires you to program a tic-tac-toe game, okay? And it's pretty straightforward, but it's also, you got to do a little bit of thinking, okay? I really encourage you to struggle through it. I've given some some tips. I write down a little bit of pseudocode to just kind of give you an idea of how your program can run and how you might want to set up your functions. And I think those should get you in the right direction. Please resist the temptation to try to search for a completed version online or something. Okay, don't copy someone else's code or whatnot. So anyway, that's been posted, and that will be due next Friday. So you've got about 10 days to work on that. Okay. Anyway, we'll get started with today's stuff. Okay. So we left off talking about if, and now we can have an else statement. Okay. So the if is you put in a condition, and if this condition is true, then the code that's associated to that condition gets executed. The else is basically if that is not true, then the code associated with the else will get executed. Right? You have to, if you're going to use an else, you have to put it on the same line as the closing curly brace of the if. Okay? So with if, we said if there's only one line associated with it, the curly braces are optional. But if you're going to use an else, you need to have curly braces. You can't just have one line and expect it to know, because it will think that the thing has ended if you just have one line without a curly brace. Okay, you can have an else if, okay, so that if this condition is false, then it will check another condition. Okay, so in this case, we have a little bit of a structure here. We say first check to see if x is less than 0. If it is, you're going to print out negative. Okay, and once you execute what's inside this if statement, it's going to skip everything else. Okay. However, if this is not true, then it goes into this section, the else. All right, and then you have another if statement. Okay, if x is greater than 0, print out positive. Okay, and in this case, with x equal to 3, it's positive. It prints out positive, and it skips the rest of the code. However, if this is false, and then this also is false, then it continues on, and it checks another else. Okay, and with the last one, there's no conditional. It just means if the first two kicked out because they were false, so if this was false and this is false, then it's going to run this either way. And in this case, we cover all situations, right? X is either less than 0, it's greater than 0, or it is 0. Okay, and that's what we have here. The thing about, and that's what we have here. It's false, so it skips this. It's false, it skips this, and it runs the last bit in the else here. If you write your code poorly, okay, as soon as one of these things gets executed, it doesn't check the other else ifs, okay, the else's or the else ifs. So in this case, I've got x is equal to 3. This part is true, x is greater than 0, so it's going to print positive and then it skips all of this, okay? Even though this statement is also true, x greater than 1, that is true. However, it never gets evaluated because it comes after the else, meaning that this is only, the computer only checks to see if this is true only if this part is false, okay? If we want it to check this, then we can't associate with an else that's going to also evaluate true. Sometimes you want to, the if-else statement that you have is just going to be a pure assignment thing, okay? So if you want to do a pure assignment such that n gets assigned to yes or n gets assigned to no based on the condition in here, then you can use the if-else, okay? So the if-else will just return the value, okay? And then generally you capture that return value to a certain thing for an assignment here, okay? If you have anything more complicated where you're running a few lines of code, if-else will not work, okay? If-else is purely reserved for, you know, if this is the case, then we want to assign this value, and if it's the other option, then we want to assign the other value, then that's when we can use if-else. All right, let's talk loops now. Okay. The probably the most common type of loop is the for loop, and in this case, what you do is you provide a vector. Now, most commonly, the vector we provide it will be a bunch of integers, like for I in 1 through 10, or for I in 1 through 1,000, or something like that. So that's often what we say. We say for, and then this is kind of just like a placeholder variable. So we'll say x or I or whatever it is in some vector here. And so the vector that we would do is the values 1 through 10. And what we're going to do is we're going to run it through cat. And so that's going to print the values x squared. So 149 up through 81, 100, right? If I didn't have cat, but I had print instead, what would my output look like? Would it be the same, or how would it be different? Yeah. If we ran print, each of these things would appear on its own line with a kind of a bracket 1. It would have bracket 1 in front of them, and each one would appear on its own line. It would be 149, and then you don't really put in a kind of a separator value or something like that. It just prints it out. If I just did cat without this space here, then all of these numbers would just appear without any spaces between them. It would just be 149, something like that. Okay. They would all kind of be stuck together. Okay, so anyway, most often the vector we give it is the numbers, a sequence of integers, but again, we can give it any vector, okay, including a list, all right? So it says given a vector, whatever it is, it just iterates through those elements in that vector. So in this case, I'm creating a list called L. The list has how many things in it? It has 3 things in it. The first is a vector of length 3. The second is a character vector of length 7. And the third is a logical vector of length 2. And so we're saying for y in the vector L. Okay? And so the first time it runs, it's going to do it for this integer vector 1, 2, 3. The second time it runs, it's going to do it for the character vector A, B, C, D, E, F, and G, and then the last one, it will do it for this logical vector true, false. Okay, and so this time, what are we asking it to do? We're just saying cat the length of y. Okay, so it's going to print 3 because that's how long the first vector element in the list is. Then it goes to the next one. The letters, it's going to print out 7. That's how long that vector is, and then it will print out 2 because that's how long the logical vector is. Okay, so this is probably a little bit different from most of your the for loops that you've created so far, but this is equally legitimate. You can give it any kind of vector. Okay, it's just most often the vector we give it is like an integer vector, but you can give it any kind of vector, including lists of all sorts of different values here. All right. Is this okay? Okay. If we load up a library called datasets, which has some built-in datasets into it, there is a file called state name. Okay, state name, it just has the names of the states, right? So the first 5 states in alphabetical order are Alabama, Alaska, Arizona, Arkansas, and California. Okay, and so what we can do is we can say for state in this vector state.name 1 through 5, which is this vector up here, we can say cat state, okay, which is, because the first time it runs, state will be the first element. So in this case, it's going to be Alabama, and then it's going to attach has, and then the number of characters in state, which has, in this case, has 7 letters. And then we want, to make it a complete sentence, letters in it, period, okay? And the /n means new line, okay? Because cat normally doesn't do new lines, right? We can use like paste instead of cat, but if you're just doing some kind of text output onto the screen, cat makes sense, all right? So it runs through it, and we've got 5 things in our vector. So the first time it looks at the word Alabama, and it figures out the number of characters, and it prints that out. Then it goes on to the word Alaska, and it prints that out, okay? California, 10 letters in. Okay, again, your vector can be any kind of vector. All right, here's just some tips regarding when you run a loop, okay? It's better to create an object to store your results first rather than growing your object as you go. Okay, this is just for performance reasons. It's okay to do it maybe in a less optimal way. Okay, it'll still run, but if you're doing something with maybe 1,000 repetitions or 1,000,000 repetitions, you might find that the computer operates faster if you do something like this. So here we're creating a vector called res for results. The results, we first create a vector where it's a bunch of NAs, a bunch of missing values, in this case 10 missing values. And then we just say for x in the integers 1 through 10, store into, subset that results vector so that the first time it runs, it's going to just look at the first element or the second element or the 10th element whenever it runs, and then store the result x squared into that position, okay? So we're using subsetting with assignment, and we're just saying, okay, store the results, and then that's when I print out the vector, okay? So when you type the name of something, you're calling the print command or print function, and so it prints it out, and it says, here's your vector with all of these values, okay? And this would be a good way to go. We'll show you some other ways that are less optimal, but is, still functions, okay? So sometimes people will just start off by creating an empty vector, okay? So here it says res is just an empty vector, and then what we do is we're just kind of combining whatever results is with the new result, okay? And so this will, R will resize the vector every single time, okay? So each one we're copying the results vector, and then we are storing it into a new redefined results vector, which is fine, it works. We get the same results, but this is a little bit less optimal. Okay, this is also less optimal. Here I just put in 0. Okay, so it starts off with a numeric vector of length 1, and then here I'm saying store in position 1, 2, all the way up through 10. okay? And every time we run it, it has to resize the vector from a vector of length 3 to a vector of length 4 to a vector of length 5, so on and so forth. And again, less optimal. It works. The end results in all of these cases are the squared values 1 through 10, but it's generally good to create your the place where you're going to store your values already sized out to what you want it to be, and then you let it run. Okay, and then you might ask, should I put in missing values or should I put in integer zeros or whatever? Okay, missing values is probably a good way to go, because if you throw in zeros, and for whatever reason, if your loop doesn't run, okay, so here, you start off with a vector of 10 zeros, and let's say for whatever reason your loop stops after 8 iterations, okay, 8 iterations, but it, based on your code, it doesn't kick back a warning or anything like that. Maybe you're just saying, for x and then you have like 1 through, and then you have some kind of thing, right, length of whatever it is that you're looking at. And so if you have up through 8 and then you have 0, 0, and you start doing some summary statistics like find the mean of the vector, now you got zeros that are going to throw off your values. Okay, if you've got missing values, NAs, and you say find the mean, at least R will say, hey, you're trying to find the mean of this thing, you've got some missing values, and it will initially kick back NA for the mean. Okay, and then you say, oh, I've got some missing values, I want to ignore the missing values, but it requires you to explicitly do that, and it will probably at least alert you to the fact that maybe the loop didn't run as many iterations as you initially thought. If you put in values like 0 that you might those could go undetected if your loop for whatever reason fails. Okay, we've got other types of loops. Another loop is the while loop. Okay, so the for, you give it the vector and it does the same thing for every element in that vector. Okay, so you know exactly if your vector has 100 things in it, you know that your vector will run 100 times. Okay, there's no questioning about the how many iterations you'll run. With the while loop, the while will continue to run until this statement, this is a conditional, until this condition is false. Okay, so if you run a while loop and this condition is always going to be true, you make a mistake and the condition you provide it will always be true, then this loop will run forever. Okay, so that's a problem. Then you have to manually tell R, stop whatever it is that you're doing, and we got to exit this thing. Okay, so in this case, I start off and I say I is equal to 1. We assign 1 to the value I. We're creating our results vector of 10 NAs, and then I say while I is less than or equal to 10 into results position I, store I squared. Okay, so I starts off at 1, and so we're going to do into results location 1, put in the value 1 squared, and then do 1 is 1 plus 1. So I is going to become 2. And then it says, okay, and then now that it reaches the end here, it goes back to the top of the loop, and it says while I is less than or equal to 10. How much is I? I is now 2. 2 is less than or equal to 10. Now it says into results section 2, we're going to store 2 squared. Then it changes, 2 becomes 3, and then it goes back, is 3 less than 10? Yes, and it keeps going. Okay, finally at the end, it gets to 10. Okay, at the 10, so I is 9. 9 plus 1 becomes 10. 10 comes up to here. Is 10 less than or equal to 10? Yes. Into results 10, we store 10 squared. I becomes 11. Okay, so I is now 11. It comes up here. It says, is 11 less than or equal to 10? Nope. And it kicks out. So if I checked what is the value of I at the end of this loop, what is the value of I? It's 11. It's not 10, it's 11, at least in this coding case, all right? If sometimes students will make the mistake of, setting I equal to 1 inside the while loop, okay? What would happen there, okay? So if let me just kind of show you. Okay, so here I've got this thing. Let me create a... All right, so here's the code right there. And then if I check, there's my results. And if I check what is I is 11, okay? If I make the mistake of putting I assigned to 1 in here, what's going to happen to my loop? It's going to go forever, right? Because I run this, okay? Well, first of all, it doesn't have, it says I not found. But okay, so we'll start off with I equal to 1 in here or something. But then I run this, and then we notice it keeps going forever, okay? And then so let's say I hit stop. Okay, and we can see I is the value 2. So what's going on is that, we start off with 1, we assign I to 1, we insert 1 into the results, and we can kind of see that right there. I becomes 2, okay, at the end of this, and it goes up to the top. Is 2 less than 10? Yes, it is, but then we reassign the value 1 to I, okay? And then so it says, okay, now store 1 squared into position 1, and then this becomes 2, okay? So you don't want to have a hard assignment here, such as I set equal to 1 inside a while loop. That's just asking for trouble, okay? Okay, so that's the while loop. We have a repeat loop, okay? A repeat loop just repeats forever, okay? And the only way you can escape out of a repeat loop is by using the keyword break, all right? Break is what's going to kick out of the repeat loop. And so inside the repeat loop, you need to have a condition that says, if this condition is true, then break. If you don't include that in there, the repeat loop will just repeat forever. So you need to have break somewhere in there. Okay, so here, this is pretty much the same thing as the previous while loop, okay? But this time, what we say is after we reassign I to be the next value, okay? So if we're at I is 9, okay? We do 9 plus 1 is 10. And then we say is if I is greater than 10. So right now at 10 is greater than 10, that's false. So it doesn't execute this part, and it runs the repeat loop again. Okay, so now I is 10, into results position 10, store 10 squared, great. Then it goes, okay, I is now 11. And then we say if I is greater than 10, so is 11 greater than 10? That is true, then it breaks out, okay? So break is the key word that says, okay, quit out of the repeat loop, okay? So again, if I checked what is the value of I at the end of this loop, what is its value? It's 11, okay? So at the end of this loop, I takes on the value 11, and that is why break got executed. Does that make sense, the repeat loop here? Okay, so we have, keywords. So we saw break. Break stops the whatever loop that you're in, okay? You can have nested loops, and so if you run a break, it's going to quit, whatever loop that that was running when the break gets executed. Okay? And then we have next. Next just ends the current iteration and goes on to the next iteration. So in this case, we have for I in 1 through 10. If I mod 2 is equal to 0, so basically if I is an even number, break, okay? Then otherwise, well, not even otherwise, okay? And if this is not executed, then it's going to run this, right? So then it cat's eye. So in the beginning, when we run this, I gets the value 1. 1 is not divisible by 2, so this code is not executed. It cats 1. Then it goes to the next iteration of the loop. 2, okay? 2 is divisible by 2, and so it executes break, and then it stops. So that's what we have here. If instead of break, I put in the word next, it's the same code as before, except I replaced break with next. It starts off with 1. 1 is not divisible by 2, so it does not run this code, and it cats 1 onto the screen. Then it goes to 2. 2 is divisible by 2, so it executes this code, which is next. So as soon as it sees the next, it does not run anything else inside that loop. It just starts the next iteration immediately. Okay, so as soon as it sees next, it says, okay, I come back up to here, I is now 3. This is not executed. It cats the 3. Then it reaches the end of the loop, so then it goes to 4. It sees the next, and it skips over. Okay, and so then we get a printout of the odd numbers. All right, so next, if you have some kind of condition inside there that says, you know what, skip this iteration, that's what it does. Okay, so as soon as it sees next, it doesn't execute anything else inside the loop. Okay, let's go back to our for loops, right? And so in the beginning, one of the earlier examples, I gave it a list, and I said for, you know, X in the list, okay? Another option, okay, you can provide it lists, and it will iterate through every element in the list. But a lot of times, you can do use subsetting, integer subsetting instead. So what we could do is basically say for X in, and this command sequence along L, this is going to produce, it's going to say L is length 3, and so it will go 1, 2, 3. That's what sequence along does. Sequence along is basically the same as 1 colon length of that object. So if that object has 25 units in it, sequence along y, if y has 25, it is a vector of length 25, sequence along y is the same as 1 colon 25. Okay, so it's 1 colon length of that thing. That's what just sequence along is. Okay, and then so if we wanted to print out the results as before, we would just say, okay, for X in 1 through 3, into results bracket X, so into position 1, put in length of list object double bracket X. So subset X, and put that in here. What would happen if I used single brackets rather than the double bracket? What would my results be? Yeah. But we're asking length of L single bracket X. So if we ask into results position X, put in length L single bracket X. And if I did that, what would my results be? It would be 1, 1, 1, right? Because we're asking what is the length of. So here, if I run this, okay, then it says 372. But if I get rid of this, because I'm doing single bracket, it's going to be a list with just one thing in it, okay? And so this code here will just be 1, 1, 1, okay? Because each of these have been subsetted to a list of length 1. Does that make sense? Okay, so if you're providing a list, make sure you're using the appropriate brackets. Okay, yeah, sequence along is just it's the same as 1 colon length of L. Okay, length of L being 3, something like that. Oh, I guess I wrote that on the next slide. So 1 through length L is 1, 2, 3. Sequence along L is 1, 2, 3. Or sequence length. This is just kind of a shorthand. Sequence underscore length, or is it sequence len? Sequence len, like you do 10, and it's going to go 1 through 10. So it's all shorthand ways of saying this, the same type of thing. Okay. All right. Basically, all of these loops that I did, these were just very simple examples, and we could just do a lot of these things using subsetting or some kind of apply function. You know, don't worry too much about efficiency. It is good to think about efficiency, but it's important to just you know, think of a solution where your code works, okay? And then after you get your thing completely working the way you want it to work, then you can go back and start thinking about efficiency, okay? R is kind of notorious or legendary for having slow loops, okay? So if you have a bunch of loops and you have loops nested inside of loops, it will probably take a very long time to run in R, okay? Very long being what, 2 minutes, okay? And, you know, depending on what you're doing, you know, maybe you have to do, you know, 100,000 iterations and then it takes a really long time. Then you can start thinking about turning your operations into vectorized operations. R works very quickly when it's when you're dealing with vectors. And so, you know, it's good to think about efficiency, but as always, the best solution is the correct and accurate solution. If it's efficient but it's wrong, then it's no good, right? So after you get it working, then you can start tweaking it, and always check to make sure that after you've tweaked it, it is working exactly the way it's supposed to be working. All right, let's talk functions, okay? Functions are very important in for any kind of programming, okay? And the way we use a function, or we create a function, is we name the function, and then into that name we store, and we say, we use the word function, and then we provide arguments, and then braced in, then we create curly braces, and then we have all the code that we want it to run. And usually at the end of the function, we'll have the function return a certain output. Okay, so functions take in arguments and then they return an output. Okay, so things go into the function and one thing comes out of the function. That's the output. Okay, if there's only one line, you can leave off the curly braces. And if you don't use the word return, then whatever the last line that gets evaluated, that will be the thing that gets output, okay? The value returned is the last expression in the function, okay? Functions themselves are objects, and that means we can work with them like any other object. Okay, so here I'm creating a function called f. F is a function of x, and the only thing it does is multiply x by itself. So multiplies x by itself. Because there's only one line, I've left off the curly braces, and because there's no return, it's going to return just the last thing it executed, which is x times x. Okay, we can throw f inside a list. Okay, and then if we ask what does that list look like, it's going to say you're inside this first kind of train car, you've got a function of x. If we ask what is the type of f, functions are known as closures, okay, which a little bit strange, but that's just what they are known, how they are stored inside R. Okay. Functions themselves can return other functions, okay? This is mostly just like a kind of a quaint example. Don't worry about this slide. You can put a note that you don't have to worry about this kind of programming here. But we can say, I want to create a function of x, and what we return is a function of y, where we are doing x plus y. Okay. And so when I do this, okay, f2 of 1, this is, I'm running the function of x of 1, and this function is going to be called, we're going to call it add 1 to it. And so add 1 itself is a function, okay? It's a function of y, where we are going to take 1 plus y. And so if we do add 1 to 7, it's going to return 8. Here, maybe this is confusing. And this is just to say that functions can return other functions, okay? So add 1 is now a function, so f2 is the function where it takes in an x and it returns an output y, right? So if I say f2 of 1, it returns a function of xy. And if I store this into the space add 1, and we ask, what is add 1? Add 1 is a function of y where we're doing x plus y. And if we check out the environment, we can actually find out that the value of x in this case is 1. Okay, so if I do add 1 on 7, it will return 8. Add 1 on 103, it returns 104. Okay. So what is this? f2 of 4. f2 of 4 is going to be a function that adds 4 to everything. And then so if I then take that function and I run 1 on it, it's going to combine those two. Okay, it's going to return 4 plus 1 or 4 plus 6. Okay, I could call f2 of 4 into a function called add 4. Okay, and then I can run add 4 on the value 6 and it will return 10. Don't worry about that, okay? Just to say, functions themselves are objects and functions can return other functions. It's something that I wouldn't say is unique to R, but is something that does make R, separates R from other languages as well. All right, we've seen this return values. If you don't, you can use the phrase return, and this will be the explicit thing that R returns, or you can leave it off, and it will be the last statement inside the function that gets returned. Okay, and in both of these cases, because there's only one line, I've left off the curly braces. But you can also always include curly braces, and that's fine as well. If you run the return statement early on in the function, then everything else after that doesn't get executed either. Okay, as soon as you execute the return statement in a function, the function sees, it views that it has completed its work and purpose in life, and it ceases to continue running the code. Okay, that's what the function does. The goal of the function is to take the inputs and return the value that it's supposed to return. And so when you say return this thing, maybe it's inside a conditional and it returns it, then it's going to be done. You can only return one object. Okay, you can only return one object. So if you need to return multiple values, you need to group them together into one object, whether that object is a vector that contains multiple values or a list that contains multiple values. Okay, if they're all of the same type, you can throw it into a vector, and that will probably keep your life easy. But if you need to return values that are of different types, you need to group them all together into a single object, and you return that object, because functions can only return one object. So in this case, we're going to return 3 values. A function of x will return the value x itself, x squared, and x raised to the third. And when we ask for f of 2, it's going to return the values 2, 4, and 8. Okay. Here is an example where we've grouped what we're interested in into a single list. And if we run it on the value 2, it returns, a list of length 3, 2, 4, and 8. Okay, and this is a named list. And of course, in your cases, you'd probably have more complicated code that gets executed before you return your object. But again, functions can only return one object, and so if you need multiple values, they have to be grouped together. And depending on the function and the operators used, you might be able to run a function on a vector itself, okay? And that's going to depend, right? If you use, if you have an if statement in there, you probably can't run it on a vector unless you explicitly give it instructions on parsing out that vector. But in this case, because the function is just only uses vectorized operations, it has no problem taking a vector as input and returning a vector as output. Okay, when we create our function, right, we say a function of, in this case we have x, y, and z. Over here we had a function, when we defined the function, it was a function of x. Okay, to create your function, you've got to kind of define what these things are, these arguments, and so you're defining what they are called inside your function, and then and when you execute the function, you can assign these things. Okay, so in this case, we're saying we want a function of x, y, and z, and all it's going to do is just going to output a character string where we've pasted x equal to the value of x, y equal to the value of y, and z equal to the value of z. Okay, so it's a very uninteresting function, but it does show us kind of how the assignment works here. So when I say 1, 2, 3, R is going to match the values in the order that they are defined in the function. So 1 is x, 2 is y, and 3 is z. Okay? But because we've named them x, y, and z, we can also define our values out of order. We can say z is 1, x is 2, and y is 3. And because I've used them here, R matches up the 1 to the z, and the 2 to the x, and the 3 to the y. Okay, and that's what we see here. And if you just use one of the names and you say y is 2, and then R will try to match up the remaining ones that aren't named into the order that it sees them. Okay, so it says y is going to be 2. Now the first value here, 1, is going to get matched up to the first thing over here, which is x. And over here, this value 3 is going to get matched up to the one after that, which in this case is z, because y has already been defined to be 2. And so we get x is 1, y is 2, and z is 3. So when you define your function, you're kind of giving all of your objects names, and you're also giving it an implied order of how R will expect to see these things. Okay, and that's why whenever you ask for help in R, and you say ask for help on R norm, okay, what you see inside the help is you see kind of the arguments and the order that we would expect to see these things. So you could say x is this, mean is this, and standard deviation is equal to this. But a lot of times we just leave those off because we're providing the arguments in the order that we expect them. Okay, and so here again, more examples of it matching it up. And then if you give it an argument that is not named as part of the function, okay, m is equal to 1, it's going to kick back an error. It's going to say, I don't know what to do with this argument m. M is equal to 1. I don't know what to do with it. Okay. A lot of times, some of the functions will contain a ... to kind of say, like, pass on any unused, undefined arguments to another part that gets used in the function. Okay, if you just define the arguments as x, y, z, then you'll need to define all 3 values when you call the function. Okay, if you can also give it default values. You can say x is equal to 1, y equals equal to 1, and z is equal to 1. So in this case, you can call the function without providing it any values, and it will use its default values. Okay, whereas over here, if I called the function without any default values, R would error out, and it would say, I don't have a value for x, y, or z. I can't run this function. Okay, so now that I have default values, I can say f of 2. 2 is going to get matched up to the first argument, so we can see x is 2, and then y and z takes on the default values. Or I can say z is equal to 3, and so 3 gets matched up to the argument z, and then x and y take on the default values. And so we get 1, 1, and 3. So we can see how R uses the arguments and the defaults to kind of define how the function gets run. Okay, this is an important topic, and I only have a few minutes left. Functions have what we call scoping rules, okay? Which means generally your function should only, all of the values you use inside the function should be provided inside the list of arguments, okay? But R is very generous and flexible when you define a function, and if you call something in the function that is not explicitly defined as part of the arguments, it's going to search what we call a higher scope, okay? So when you call a function, it takes all of its arguments and it includes it, it puts it in its own little kind of world, its little environment. And then and the function will try to draw all of its values that it needs from that little environment or scope that we've created. If it can't find it, then instead of erroring out, it's going to say, all right, I'm going to expand my view of the world and just search for this thing, right? So here I've defined f as a function of x, and so when it tries to evaluate x plus y, well, it finds the x because that's something we're going to give it as an argument, but then it says, okay, now I've got to find y. I don't see y in here, okay, right? We call f of 3. 3 gets passed in as x, so I got 3 plus something, and it says, okay, I don't find y here, and in this case, it's going to search the global environment because f is defined in the global environment, and it says, I found something called y. Y has the value of 1. I'm going to add those two together and give you the value 4. Okay? Over here, I have y in the global environment. Inside the function g, I'm going to define y is 2 inside the function g. So again, imagine this is kind of its own little world here. And so I'm going to call g of 3. 3 gets passed in as x, the value in their argument. Then it says x plus y, okay? Inside its little world, it says, oh, I've got x is 3, and then right here, y is 2. So it's going to take that 2, and it's going to take that and add 5. It's not going to bother trying to search the global environment because it is happy it found y where it needs to be, okay? And if I ask what is the value of y after running this function g, it's going to still have the value 1, okay? Because what happens kind of inside the little function environment doesn't affect what happens in the global environment. All right, and we'll talk about environments and these rules more in depth, okay? So yeah, we'll stop here for now, okay? And we'll see you guys on Friday, and we'll continue our discussion of stuff.